Hello everybody. Today in this video we're gonna complete we're talking about the topic of getting the roots of algebraic equations. And today we're gonna start with the bracketed methods, and the first one of the two methods is the bisection method, which we are gonna talk today about. So I'm gonna first start with the basic idea and how we can understand this graphically, and then how we can move to doing this numerically, and then to do this by Excel. And actually this method is based on a very simple idea, which is if we have a function like this function that we have here, it has part over the x-axis and part below the x-axis. So the part above the x-axis, we all know that it's the part that has f of x is greater than 0, and the one below has the f of x smaller than 0. And we know that the root is the point that is in the midpoint, or is at the exact interface between the top and bottom, where the function is 0. So let's say if we pick one value of f of x in the top, that has a positive function f of x, and then another x that corresponds to a negative f of x. Then we know that because this is in the positive part and this is the negative part, so the function must have passed by the x equals 0 axis, or the x-axis. So we know that the function, or the root, is somewhere between this x and this x. And this is why it's called the bracketed method, because you get two values and you know that the root is sitting somewhere between these two. So you have the bracket, the right and left bracket, which is this x and the other x. So to do this mathematically, we can say that if we have this condition of f of x1 multiplied by f of x2 is less than 0, means that one is positive and one is negative, which is exactly what we saw in the previous graph, that one is positive and one is negative. Then the root is sitting somewhere between this x1 and x2. So it's very simple and straightforward. And the way the bisection method goes is you can somehow know how it works by just looking at the name. It says bisection method, and actually what happens is that you get this distance between the two x and get the average value. You get the cut it into two halves. That's why it's called bisection method. And in the middle part, you will have another x that is somewhere closer to the root, and then you calculate the function of x, and which is f of x average 1. And then you have another point that is somewhere closer to the root, and you need to know if it's closer, if it's not, and how can you get to another step where you can get a closer point. So what happens is you do this calculation again. You do the f of x average 1 multiplied by f of x1, and f of average x average 2 multiplied by f of x2, and see which one is positive and which one is negative. So from this graph you can tell that these two are negative, so the root is not sitting here between them, and this is negative, this is positive. So from these two conditions you can tell that from f of x1 multiplied by f of x average 1, that the root is in the somewhere between x1 and x average 1. So you do the same thing again. You have this new point, which is x average 1 and x1. You do the same steps. You get the midpoint, the average value between x1 and x average 1, and do the same thing. You get f of x average 2, and then you do the same thing, multiplication of f of x average 2 by f x1 and by f average 1 x average 1, and then you get, you know, that the root is sitting somewhere here, and then you do the same, so on until you get a good value that you will be happy with. And you can have a condition, and you can keep going and repeating these steps until you reach this point when you calculate what's called the percent relative error. It's called relative error because it's relative to the previous value, because you do not know the exact value while you're working. So you get the absolute value between the new and old divided by the new value, and get the percent of this, and this can tell you how accurate is your result and how closer you are getting to the final result. And just one thing that we need to keep in mind is that you have to keep in mind that the shape of the curve really has a big impact on the efficiency of this method, or the bracketed methods in general. So you might have two positive values and you might not have any roots, or you can have an even number of roots. So it's not a condition that if you have two positive roots or two positive values that there is no roots in between. You can have two, you can have four. It depends on the shape of the curve, and the opposites for the odd number, when you have two roots with different signs, the multiplication is negative. Then you might have 1 or 3 or 5 or 7, whatever the number of roots, and the shape of the function dictates this. So there is kind of limitation to this method, and you can somehow make yourself more accurate or more confident with your result if you pick any random or regular values and calculate the corresponding f of x of each, so you can know when the sign will flip from positive to negative or from negative to positive. I'll show you that in the Excel sheet when we start. But just as something that you have to keep in mind while working in Microsoft Excel, how we can do this. So let's say we will set up our Excel sheet as this. You will have a column for x1 and x2, and you calculate the average based on x1 and x2, and you calculate f of x1, f of x average, and f of x2, and then you calculate the error. We can skip that now, but we are more concerned with these. So what we are gonna do is to multiply these two values of f of x1 and f of x average, and f of x2 and f of x average, and you see if these two conditions apply. You have these two multiplied by each other is greater than 0, and this is smaller than 0. So if this is the condition, then this means that the root is somewhere between x average and x2. So you want in the next step that the two values that you're gonna get the average of is b and c, which means that you will if these conditions do so we'll be doing an if conditional thing in the Excel sheet, and so you will make this b go here and c goes here, and the same or the same case if the opposite conditions apply. This is negative and this is positive, so the root is somewhere between x1 and x average, so x average will be the new x2, and then x1 will be the same x1, and so on and so forth. So it's gonna be just setting the first one or two rows, and then you're gonna drag this thing till 30, 40, 100, whatever number of iterations you wanna make, till you reach your accuracy that you want. Now let's see how we are going to do this in Microsoft Excel. So this is the example that we are going to work with. It's the van der Waals equation for benzene. I wrote the equation in this way, and then I rewrote it in this way. It's just rewriting the equation after rearranging it so that it's something equals to 0, so we can work with the bisection method now. We have the constants of van der Waals for benzene, which is these two, A, B, A, and B, and the conditions of pressure, temperature, and of course the gas constant. So it's very recommended that if you can have an estimation to the solution, it will really help you to get closer. As you get closer with the or you start with a close value, this will make the number of iterations smaller and the conversion easier. So we know that we have an equation that's not very accurate, which is the ideal gas law. So you can calculate an estimation by just calculating the value of V based on the ideal gas law, and from the ideal gas law you can tell that the V equals, we know that PV equals RT, which is V over N, so you have RT over V, which is R multiplied by T over P, so you have the value of 2.05. So we are expecting ourselves to be expecting a value around 2.05 or whatever the value that we're gonna get. So here this is the thing that I wanted to or I discussed before in the previous slides. So you can make a table for v and f of v, which is this equation that I just wrote, and see. So I can start with 0, which is a value that is meaningless, but just to start with, and calculate the function of v. What I'm doing here, just to make it clear for you, I'm picking some values, so I'm sure that I'm taking two values of the v where the f of v is flipping from negative to positive, so I know the root is in between these two. Because if you pick two values with the same sign, then you're not going to reach the solution anyways. So this is what I'm doing now. So I'm just now substituting in the equation. It is b and then the dollar sign multiplied by v power 3 minus the same p and the dollar sign multiplied by b and the dollar sign plus r dollar sign multiplied by t and the dollar and the dollar sign, and then multiplied by v power 2 minus a and the dollar sign multiplied by v plus a dollar sign multiplied by b and the dollar sign. So this is just calculation of the value. I'm gonna make a 0.5 interval. You can make it more or less based on whatever you want. So I'm gonna go till 5, anything. I can just see it by visually that you have here change in sign, so you have something between 0 and 0.5, and you can see a change in sign here, which is between 2 and 2.5. You can do this visually, or you can do this by making a condition. You can say, is there a root, and simply you're multiplying this by this and getting the value. Or you can make it even easier. You can make a first if conditional. You can say if this multiplied by this is greater than 0, then you can say that there is no root. I think we need to put these no root and then a root. Okay, so you can see from this, again, I like to make everything centered. I'm sorry for that, but this is how I like to see my Excel sheets. Okay, so from this you can tell that there is a root between 0 and 0.5, and there is a root between 2 and 2.5. And again, we said that in the previous video, and it's very important to know that you will have some values and some roots that are mathematical roots. They don't have any physical meaning, and you have to understand that well, and make sure that you do not just take any value as the right value. It's depending on your understanding, and that's why it was very important to do this, so you know that this value is not the right value. That's between 0 and 0.5. The right value is somewhere between 2 and 2.5, because this is the closer to the value. So the take-home message is that we're gonna take these two values as the x1 and x2, the two starting values, and then I'm gonna make the same table. It's v1, v2, and v average. And just make them look somehow professional and look better. So this is the first thing that we're gonna do, is to put the values of 2 and 2.5 here, and then in these three cells we're gonna calculate f of v1, f of v2, this is v average, and this is f of v2. So this is almost the first, or the important things that we need to calculate. And then I can take this v, I can take this v and substitute with it here. I just move this v, it is here, and this here, and this here. Okay, so I'm now calculating this from f of v1 from v1, and f of v2 is calculated from v2, which is 2.5, is giving the same value, so I'm calculating it right. And the v average is average of this and this. Okay, so we can see from here that this there is a flip in the sign, and this v average is somehow in the average, or in between these two values. And now we come to the if condition. This is the most critical part of the Excel sheet, which is doing the if conditional the right way. So I'm gonna say if this multiplied by this is greater than 0, which is the case now, then we know that the next v will be somewhere between v1 and v average. So I want this cell to be this, otherwise I want it to be v average. And the same here, equals if this multiplied by this is I'm sorry, I did something wrong. If this is, smaller than 0, and we do here another if conditional based on the other two, or the other multiplication. If this multiplied by this is greater than 0, then this will be the average, otherwise it will be this, and it is done. So we now know that we are calculating this value based on these two values of the 2 and 2.25. So this is the new point, and we recalculate the average. And now we can calculate the percent error based on what we have now. So let's make a new cell or new column. It is percent error, and we agreed that this is gonna be the absolute value of it was the new minus the old, so it will be this minus this divided by the new value, and this is percentage, so it's gonna 0.000 something. Okay, let me just make this look better for me. I'm sorry, I cannot hold myself. And we can drag this here. So you see, it's doing everything as we want. Now you see that this value of the f of v average, which is the should go to 0 at the end, is now negative 0.00 something, and the error is 3 point something times 10 to the minus 8, which is really good. You can do this million times, it's not any problem. And you can calculate the number of iterations here if you want. Just to know, I'll fill this here is, just to know how many iterations are you making. It is, we're done. We have everything then now we know how many iterations we did, and it's gonna take care of everything. And the cool thing about this thing is that you do not need to change any formulas if you change the values. So it's gonna be 2.209 and it was 2.05, which is close. Now this is surely more accurate. But if you just want to change it from the 2 to 2.5 or change it to 2 to 2.3, then you'll see it's doing everything. You're reaching the same value, it has more accuracy, but you didn't do anything but just changing the value. And if you wanna go back to the 2.5, it's okay, there is no problem at all. There is one thing we're gonna do now, which is just for comparing this method to the other method. So we're gonna make a plot of the number of iterations we make and the percent accuracy we get. So we're gonna do this as what is wrong? Let's insert scatter. I think I have to do it myself. Okay, so this is I'm gonna edit this. I'm gonna call this as bisection method. The x values are these and the y values are these. So I'm plotting the percent error I get with against the number of steps of iterations. And because it's going into really smaller values, so I'm gonna do this with the logarithmic axis, so you can see easily how many steps are you or what's the accuracy or the percent error you're getting. So you see from here that you needed almost 30 steps to reach the accuracy of 10 to the minus 12. And we will see when we use the next method and the rest of the methods that we're gonna discuss how some methods will do or reach the same accuracy level in 3 or 4 steps, because they have different approach, or the way of solving this is more easier. So this is everything for today, and in the next video we're gonna discuss another bracketed method, inshallah. So I'll see you then. So, bye bye.